So what? So alpha is a lower bound of E. Right? Because anything less than alpha is not in E. So this must be a lower bound. Yeah? And now how do we prove that nothing bigger than it is not a lower bound? So that's part one. Yeah, it is part one. Okay, I was making sure. Yeah, let's call this I again. So now I have to show the second thing, which shows anything bigger than it is not an alpha. Well, anything bigger. So now we do the other part, right? So now we want to now we want to show if x is greater than alpha. Well, x is not an alpha because alpha is the supremum, right? Are you guys with me? I can't tell. There's a lot of quiet, a few heads nodding. Pretty sure I'm killing somebody in the back. Well, that's cool. We'll stop and talk about it. So x is not an L. So, because it's the supremum, so there exists, sorry, yeah, I always have to get this right. There exists x in E such that x, or wait, hold on. If x is greater than a, blah, blah, blah. So there exists, let's say y in E such that y is less than x. So this means that, so x is not a lower bound. So this actually completes the proof. But let me step back because I know this is kind of confusing, but I'm going to re-explain everything. Are you guys with me, or do you need me to go through this heuristically? Yeah, in the back.
I'm not seeing 100% how you went from x is not a need to so alpha is a lower bound of E.
Well, okay, so that's a good point. So what do I want to show here? The first thing I wanted to show is that x is a lower bound for E, right? So if you want to show, right, the two things I have to show is to show alpha is the infimum. I have to show alpha is the lower bound, and alpha, anything bigger than alpha is not. Does that make sense? Okay. So I'm going to show you alpha is a lower bound. So what I'm going to do is I'm going to take something smaller than alpha. Or so okay, let me maybe step back. So to be a lower bound, it means nothing smaller than you is in the set. To be a lower, if x is a lower bound of E, nothing smaller than, or if alpha is a lower bound for E, nothing smaller than alpha is in E. Right? So I'm going to take something smaller than alpha and show you it's not in E. Does that make sense? So I take something smaller than alpha. Now this guy, it's not an up, so since x is not an up, so this is where I'm using that x is not the supremum. Alpha is the supremum. We defined alpha as the supremum. X is not the supremum because it's smaller than alpha. Since x is not the supremum, there is something in L such that beta is bigger than x. I'm trying to explain this poorly. Okay, maybe I'll draw a picture. Pictures sometimes help. So back to the horrible picture I drew before. This is L, this is E. And I'm trying to show you that the least upper bound of L is the greatest lower bound of this. So I have to show you two things. I have to show you that whatever point I get here is in fact smaller than or equal to anything in E. Right? So let's do that first. So what I'm saying is, so what I'm going to do is I'm going to show you there's nothing in E over here. So I grab a guy here and show you, well, the argument is since this guy is here, he's not the biggest L, he's not the least upper bound of L. So there's something in L to its right. But everything in L is less than everything in E. Yeah, it's a little tight. Let me see if I can. I see why it's confusing, but I'm trying to explain it another way. Okay. Yeah, this is one of those things I think you might just think about a little. Let me see if I can include an extra line. Here, so let me include an extra line here. So we have that if beta is in L, beta is greater than x. But beta is less than or equal to all elements of E. Why is this true? Because, okay, so again, we took the group of all lower bounds. So once you know something is in beta, everything to its left must not be in E. God, I'm mixing up all the letters now. Once I know something's an L, if I grab a guy in L, everything less than it must not be in E. Do you agree with that? Because this is the set of lower bounds.
If you grab a guy in L, anything less than that guy
Will not be in E.
So lower bounds, right? So
Yeah,
you
yeah.
go all the way to the left. We grab a guy even lower than that.
They'll be in L, but not E.
Yeah, they're not going to be in E.
That's exactly right. And that's what I'm saying here. I have found a beta bigger than X. So X is to the left of beta. So X could not have been in E. So that's why I conclude X is not in E. Because you're right, X is in L. I agree with you, X is in L, but X is also not in E. Because he's to the left of beta. Does that make sense? Yeah, the reason this proof is confusing is because I'm using contrapositives left and right. But this is like the shortest version of the proof. If you want, I can go to all the details. How about this? Talk to me after class, and I'll gladly go through with it with you again. And it's not too bad. There's a lot of like reverse logic being used in there, because I'm using it twice in the same sentence. So I understand why it's confusing, and I mean it took me a second to say it correctly. But let's talk after class, and we'll talk about it then. Great, but for the most part, this makes sense. So the point is, once you have the least upper bound property, and this is for any ordered set, I haven't said anything about ordered fields. Once you have the least upper bound property, you have the greatest lower bound property. Which means in R, as you'll see in a second, everything has a sup and an inf, as long as it's bounded. Okay, if I tell you 5 is bigger than everything in this set, negative 7 is less than everything in this set, that set must have a sup and an inf. That's simple. Great, so let me just finish this up quickly. So I'm actually not gonna, I think I might skip the proof of that one really, have you guys read the book at all? There's that one really nasty theorem about the nth roots. What I'm gonna do is state the theorem and state 3 lemmas, probably prove the 3 lemmas that you need to prove that, because he only states the theorem and assumes you understand those lemmas. I'll state the lemmas, and if we have time, maybe I'll go into the proof. But it's not that bad, it's just a bunch of calculation. It's a good homework assignment though. Yeah, okay, fine. So anyways, I want to move on to this theorem. This is the big theorem for like this week. There exists an ordered field. Let's say we call it R, with the least upper bound property. Moreover, Q is contained in R. And this is what the real numbers are. The real numbers are this ordered field that contains Q that has the least upper bound property. And in fact, we're going to make better sense of this. We're actually going to prove R is the only ordered field that contains with the least upper bound property, just about. And we're going to say it in a different way. We'll prove that R is the only complete ordered field. The word complete doesn't mean anything to you yet. But in fact, R is the unique thing that does that. That's why it's so pretty when you use it. I mean, you don't believe me, but it is extremely useful. All right? How am I doing time-wise? All right. So I'm gonna go through. Let's see how I'm gonna do this. I'm gonna go through 2 quick proofs. I want to prove 2 of the most important properties of R right now, and then I'll mention this theorem, this nth root theorem, that I don't think I'm gonna get to because the proof is long. Well, whatever. Maybe I could just take an extra day. Maybe I'll cover it tomorrow. But I'm gonna state. I'm gonna give you specific homework for tomorrow. There's this theorem. I can find the number if you want. It's theorem 1.21. I want you to try to read through that proof. I'm going to give you the lemmas you need to prove it. So assuming the lemmas, this proof follows through. Yeah.
So are you going to define R?
So that's the point. Is the proof of this theorem is building R. Is you literally take Q and build R as a power set of Q, or as a subset of the power set of Q. And you do this really. It's really neat. The proof is this dedicate cuts, but this proof takes 5 written pages. I promise you that would take me the greater part of an hour and a half. So I just don't think it's that. Everyone here believes in the real numbers, I hope. So I'm just going to assume we did this. And if you really want to see it, it's the appendix of chapter 1. I might present it later. The proof's extremely long. It's extremely technical. And it's like, this proof is nothing compared to how confusing that gets sometimes. Like I have to sit down and work through the details to get it myself.